Hi there. In the last of this summary videos on organic chemistry, I want to look at organic chemistry reactions and specifically give them not new names but group names for the type of reactions that we had a look at. The first group of reactions I want to look at are called the addition reactions, and these are specifically to organic chemistry. Okay, we have addition reactions. Now, addition reactions refers specifically where I add an atom or a functional group or something to that extent to a single molecule. So the different addition reactions that we had a look at was the hydrogenation of alkenes or alkynes. Okay, so you'll remember that alkenes and alkynes were unsaturated. These are unsaturated, and unsaturated means that all the carbons do not have the maximum number of hydrogens. So if we add a hydrogen, okay, addition, if we add a hydrogen, we hydrogenate the molecule. Okay, so that was hydrogenation, was when we when we had an alkene or an alkyne plus a hydrogen. And that produced an alkane, which is a saturated hydrocarbon. Now the reaction conditions here, if I can write it here, and here I start with my messing up again, okay, but the reaction conditions, okay, one is that the alkene or alkyne is dissolved in a nonpolar, because it is nonpolar, in a nonpolar solvent. Okay, polar solvent with catalyst, platinum is a good one. Platinum, for example, in H2O, in a hydrogen environment. Okay, a hydrogen environment. Okay, these were the reaction conditions for this to occur, and now let's move on to the next one, which was when we added a halogen. Okay, so next we could add a halogenation of alkenes or alkynes. Alkynes and halogenation involved, let's stick to alkenes. Okay, let's just do haloalkation of alkenes, and that is where we have an alkene plus a halogen. So again, you can see it's addition because we're adding a halogen to the alkene structure, and this produces a haloalkane. And obviously if I have an alkyne and I do the same thing, I am producing haloalkene. Okay, so in this case, what happens is the halogen is X2. There's two halogens. There's a double bond. The one double bond breaks, taking one of the halogens. The other one takes the other halogen, and that is called halogenation. We're adding a halogen to the alkene structure to produce a haloalkane. Okay, the reaction condition for this one is fairly simple. Okay, there's no reaction condition. Condition is the halogen is added to the alkene. Okay, and not the other way around. The halogen is added to the alkene. Okay, that is halogenation of alkenes, but we also did hydrohalogenation of alkene. Okay, hydrohalogenation. So in halogenation, we made of an alkene a dibromo or a dichloro, because we have two chlorines or bromines or iodines or fluorines, and so it is di, meaning that there are two carbons that will get a halogen. In hydrohalogenation, we are adding both a halogen and a hydrogen. Okay, so again we have hydrohalogenation takes an alkene plus HX, okay, where X represents a group 7, producing a haloalkane. Again, but this time it is a haloalkane where only a single, so we had a double bond here. That double bond breaks, and the one gets a hydrogen and the other one gets the halogen. Okay, reaction conditions for this one. The reaction conditions for this one is very similar. Okay, let's just write our C reaction conditions. Add the H, the hydrogen halide. Okay, that's what we call a hydrogen combined with a halogen, hydrogen halide, to the alkene. So that is what we're going to do, but no water present. No water present. Now, why would we say no water present? Because usually we dilute this in water. Usually this is diluted in water, and it's diluted in water because it's an acid, so it's diluted. And if I do dilute it in water, the problem will now be that the water will react to the alkene to produce an alcohol, which is the next reaction that we are going to look at, is the hydration of alkene. Okay, hydration of alkene. Okay, so the hydration of an alkene is where I take an alkene and I add water to it, H2O, and that produces an alcohol. Okay, that is called the hydration of alkenes. Okay, and the reaction conditions for this one, is an excess of water. An excess of the water is needed, plus a small amount of an acid, either a hydrogen halide or something like H. It has to be a strong acid, okay, of a strong acid, H3PO4 for example. Okay, strong acid, and this will act as a catalyst, okay, to favor the reaction. Okay, and this would be the reaction conditions for the hydration of alkenes. In other words, producing an alkene or producing an alcohol from an alkene and water. Okay, now these are all the addition reactions that we are going to look at, and now the opposite of addition is elimination. That would be the next set of reactions we're going to look at. Now the elimination reactions that we looked at would be, the first one would be dehydrogenation. That is an incredibly long word, but I think you really understand very well what it is. Dehydrogenation means I am dehalohydrogenating my organic compound. In other words, I've got a halogen and a hydrogen that is being removed. Okay, and so elimination reactions refer to removing an atom or functional group from an organic compound. Okay, sorry for all my abbreviations. That's just to keep this as short as possible. Okay, and then the dehydrohalogenation means I start with a halogen, I start with a haloalkane, and then from that haloalkane I've got some reaction condition which I'll explain now, and then the product of this would be an alkene plus a halogen halide. Okay, so it's literally the opposite of halohydrogenation, and the reaction conditions here was, so the reaction conditions, what was it, a concentrated solution of pure sodium hydroxide, and then this sodium hydroxide is solved in pure ethanol, and then it is heated with reflux. What that means is that the vapors produced from heating this solution returns, vapor condenses and returns to the reaction vessel, condenses and returns to the reaction vessel. Okay, in other words, just the container that we're using to do this reaction in. The other elimination reaction we look at is dehydration of alcohol. Okay, and that means we are removing a water molecule from an alcohol. Okay, how are we able to do that? So let's look at that. We've got our alcohol, and then this is a reversible reaction. Okay, that's why we have two arrows pointing in either direction. It produces an alkene plus water. Okay, and that is why this is called dehydration of alcohol. The reverse reaction, if I add water to alkene, we saw before, that's the hydration of an alcohol, and this one is done under the following conditions. So this one's reaction condition is that the alcohol is heated with a concentrated solution of a strong acid. So usually sulfuric acid is used, and obviously this strong acid acts then as a catalyst, since it's not either a reactant or a product in here, although it's actually both. Okay, that's why it's a catalyst. It is both a reactant and a product. It has intermediate steps that it reacts to, but in the end it just produces the acid again. Okay, that was the one way. The other way was also to let alcohol, this is one, or let alcohol vapors pass through some sort of catalyst like aluminium oxide, and this also had the same effect. Okay, so these are the only two elimination reactions we looked at, even though you do get a reaction called dehydrogenation and dehalogenation. Okay, so it is possible to do those two as well, but we're not looking at it. And then the next type of group of reactions that we looked at was substitution reactions, and these were reactions wherein a functional group is substituted, let's call replaced. Let's use is replaced with another functional group. Okay, the ones we looked at is going from alcohols, from an alcohol, let's change color, from an alcohol to a haloalkane. Obviously that means I am replacing my OH. I'm substituting OH with halogen. Okay, and the way this is done is, or actually the whole reaction is that alcohol is treated with hydrohalide, and the product produced is a haloalkane. Plus water. And why does it produce water? Well, remember, water is H2O, which means that we can see where the OH comes from. Okay, so this is some substituent bonded to OH plus HX, and that produces a substituent bonded to halide. So what happened to the OH and the H? Well, they produced H2O. Okay, so this was the reaction. The reaction conditions were that we usually use tertiary. It works best with tertiary alcohols. Now tertiary alcohol is when I have my substituent OH is bonded to a carbon, and now this carbon has 4 other bonds. If it's bonded once to another carbon, it is called a primary. Primary means that carbon is bonded to one carbon. If it's bonded to another carbon, Okay, in this case it means that there's at least one branch off of this carbon. There's at least one branch. Okay, or there is well, that would be a secondary. It's not really a branch. Secondary has two carbons. Okay, that just means that the alcohol is not at the end. It is somewhere. Notice if I didn't have this one, then my carbon is at the end, either on this end or on that end. The carbon is at the end. If it's not at the end, it's somewhere in between, which means it's bonded to one of the carbons in the carbon chain, not on the end of the carbon chain, because that carbon is bonded to two other carbons. That makes it a secondary alcohol. If now this carbon is bonded again, so on all three of the other valence electrons he has carbons, this is a tertiary alcohol, and tertiary alcohols are very reactive. Okay, well, not very, but much more than the primary and the secondary alcohols. And so this time, not only is the hydroxyl ion in a carbon chain and not on the ends, but on that carbon chain, on the carbon it's connected to, there is another branch. Okay, so that makes it a tertiary alcohol. And then this is conducted at room temperature. Okay, now if we were to use as primary or secondary alcohol, the temperature would be much higher and the reaction will be slower because they are less reactive and therefore need more energy. We'll have to increase the energy and it happens slower. Okay, that is going from an alcohol to a haloalkane. Okay, the next one we did was to do the reverse of that, going from a haloalkane to an alcohol. And in this reaction, what we had was a haloalkane plus a base. Okay, now you don't know what bases are necessarily yet, but the two strongest bases that we will look at is sodium hydroxide or potassium hydroxide. Okay, and this produced for us a haloalkane, sorry, not a haloalkane, an alcohol, which is a substituent bonded, sorry, this should be substituent, that was a halogen halide, a substituent bonded to an OH, and it has a product of producing a halogen halide as well. Okay, again, why that? Well, it's rather simple, and it then produces a salt, and that salt would be the product of whatever base we use, and so for example NaX or potassium X, whichever halogen we have. Okay, so reaction conditions for this one, okay, there were 3 steps here. We dissolve our haloalkane in ethanol. Okay, 2 is we added an aqueous solution, of the base, okay, and then 3 is we added heat to the reaction. Okay, and which means that we again had vapors, and those vapors were condensed and produced our products Okay, so these are actually all of the reactions we looked at with so we've got 3 types of reactions: addition reactions, elimination reactions, substitution, and then there was one last one that we haven't looked at yet, and that is called synthesis. And there's only one reaction that we used in synthesis, and that was synthesis. And synthesis means to produce. Okay, to synthesize means to produce, and we looked at Fischer esterification. Fischer esterification. Now, in Fischer esterification, we took an alcohol. We took alcohol plus a carboxylic acid, and that produced for us an ester. And the reaction condition was very simple: a concentrated H2SO4. Okay, we use the concentrated solution of H2SO4 as our catalyst, and this is how we produced an ester. And the ester is there for, remember, an ester has a carbon double bonded to an oxygen, single bonded to a carbon. And so here I've got my alkyl substituent, or an alcohol, which has more or less a structure like this one, and let's call this R1. And then we had our actually R1, let's number it at the top. And then we had our carboxylic acid, which is a carbon double bonded to an oxygen, single bonded to an OH. Okay, so that's our carboxylic acid, and it also has a substituent. Let's call that one R2. And then the ester that is produced is a carbon double bonded to an oxygen, single bonded to another oxygen. Sorry, I messed up there. And then this oxygen has another valence electron that is now connected to the alcohol R1, and this carbon on this side is bonded to R2. The hydrocarbon chain that was associated with the carboxylic acid. And in naming this ester, I think it's a good place just to remind you how to name this ester. In naming this ester, we had an alkyl group that was associated with the alcohol. Okay, and we had an alkanoate that was associated with the carbox acid. Okay, this one was associated. So in other words, whatever we call, or whatever this substituent is, became an alkyl group, a normal branch off of this thing. This would be named as if it was a branch, which it is. And then the carboxylic acid part will now, instead of being carboxylic acid with an alcohol, it is carboxylic acid with a branch. It now becomes an alkanoate. It gets the suffix oate, and the alkane would just be represented by whatever you call R2 here. Okay, so that is me for reactions, okay, and reaction conditions. I hope you found this useful. See you in the next video.